Morning, everyone. How are we doing so far? Any questions, concerns, frustrations? Oh, good. Don't even mind the rain coming in. It's kind of nice. I'm from Oregon, remember, so it feels a little bit more like home. Okay, so we're going to kind of pick up our pace and go right into the course content. I I adjusted my schedule. I had some other things change, so and I also wanted to look at what would be the most beneficial way to address everyone's needs and learning needs. So I've broken up my office hours on Tuesdays and Thursdays. So I'm going to do a half hour before my first class at 7 o'clock in the morning, so that if they have questions, they just come in early. We'll do it, and I'll do the other half hour after this class. So right after class, 10:15. We'll see how long we can stay in here. There's probably another class. If not, we'll go out. We'll figure out. If you got questions, we'll do it. If we go over 30 minutes, that's probably okay. Right now I don't have a second class. I do have a 12 o'clock class at another campus that starts next month. But other than that, for right now, if you've got questions, we can kind of continue and get them answered. Like I said, if there's not another class, we could even stay in here, but I have a feeling there's probably a class right after ours, so we'll make that work. So today, to sort of catch up, we put this all on paper of what we need to do. We need to do about 3 sections a week, and that's because they design it for a Monday, Wednesday, Friday class, meeting 3 times a week. Then you do 1 section per day. We have a little bit extra time because we're doing 3 days in just 2 days. So we'll take a look, and I think we'll be pretty good. We'll do the 1.3 and the 1.6 today. So we're going to take a look both at more functions and then transformation of functions, what all that's about. And then that'll set us up for Thursday. We'll look at 1.7 and 1.8. Due dates, if there are due dates in Canvas, which there might be, I copied somebody else's Canvas course over, and so those due dates I'll examine, but they're not really what we really want to work towards is whatever the due dates are in our My Math Lab, right? So those are kind of the determining ones. I can move those as well, so I'm not saying that those are all in stone or anything, but those typically what happens is once most systems, it's been a while since I've used My Math Lab, most systems, once that due date passed, you can't access the homework anymore. Or if you do, they don't give you points, those kind of things. So we'll work with it, but the goal is try to kind of go off of the syllabus calendar wherever we're at within a few days or by that weekend. So the goal would be, by the end of this weekend, because maybe you study, you do these things, but you sit down and do your homework on the weekend or something. So on a weekly basis, they'll try to keep up with where we're at. And again, it doesn't mean you've gotten all the problems done, but get at least get as much as you can, and then also know where you have questions so we can get those answered, right? So that's the goal. I met with our recitation teaching assistant. She's doing a master's program in applied mathematics. Really nice. I think you guys got a really nice TA. So she'll be working with you, and we kind of talked about what the recitation will be. It'll be your opportunity to kind of work in small groups to talk through problems. She'll have printed worksheets, and they go over some of the skills you need that we don't necessarily teach in this class. Like I think the first activity she had for you is going to be on factoring. So you do some practice with that because we use it here, but in here we assume you already know how to do it. So there's those opportunities. But anyway, half of you will meet her today at, I think you guys, 3 o'clock or so? Yeah, in the afternoon. And then on Thursday, the rest of you who have the Thursday recitation will meet her at that time, and she'll get you up and running. But her office is on the same floor as mine, so we can keep in touch. But basically, I told her she's the one that runs that recitation. That's 20% of the grade. So whatever she says goes. I'll support her on that. And then I'll take care of all the other parts over here. So anything with My Math Lab, talk to me about. I can address all of those. I'm not going to have her. She'll just be involved in the worksheets and the recitation, exams, and everything else. I'll handle over here. Okay. Let's go back here. And I do have some notes that I need to look at these notes. I don't want to inundate you with resources that are maybe not applicable, but also, again, these were from another Canvas course. So I'll look over those notes for 1.2 and 1.3, and if they look like they might be helpful, I'll make them available. But I also don't want to inundate you with too much. So I wasn't sure if these were the same, but I'll look over those. Same thing with 1.6. These items you see down here are not available yet, but I'll take a look. And let me see what, I can't remember how far I got. So for 1.3, I've shared a video, a pre-recorded video that I use in my online course, so properties of graphs, and I'll go over my lecture slide deck, and there's some notes here. So again, each section will eventually be set up like this. I can't remember how far. I'm not even sure if I got 1.6 set up yet or not, but we'll get there. We'll do that. So there's these notes which may be valuable. Again, you can print them out if you want. You can download them however you want, but you'll see some of these as examples in the lecture notes. Some maybe not, but it's almost like a little textbook, right? So those are there, but we'll go ahead and go through this lecture to give an introduction to this content. And again, this is what the recorded lecture is based on, so we'll do that. I'm also recording now, so that's why I have this Bluetooth on. I forgot it for my class yesterday, and there's a lot of background noise. If I just use the other microphone, this has a noise canceling, so it sounds much better without having to do much access, so that's why I'll make sure I have this with me. So we're going to look at properties of graphs here, kind of continuing on from what we talked about on our first day. So a couple things that a graph can do. It could be increasing. What does it mean to increase?
We always look at it from left to right. It's kind of like the
Good.
way we see it from left to right.
So we see it from left to right, which means x is always increasing. So that's the first thing. So that's not what we're talking about as an increasing function. What is increasing when we talk about an increasing function? Since x is always increasing, the y value has to be increasing for the function to be defined as increasing. Because again, left to right, x is always going to be increasing. So that's an increasing one, is that the y values are getting bigger. A decreasing function, the x's are still increasing because we're reading from left to right, and you have to do that. I'm ambidextrous, which means I can use my left and my right hand regularly, and I do read actually in both directions, which is great. But when you go for a graph, it's going to be very confusing because I said, is it increasing or decreasing? Well, it depends on which way I read it, right? So force yourself to read graphs from left to right, and then all these definitions fit. But again, it's a skill to be able to do things in two directions, but it's also a skill that can kind of get in the way of reading mathematical graphs. So a decreasing function just means when we go from left to right, the y values are decreasing. Okay, so that's kind of our definitions. Constant function is that horizontal line. The y values don't change. X values are still always increasing from left to right. So that's always a given, because we're going to read from left to right. But it's so when we talk about increasing, we're talking about what's happening to the y. Increasing, decreasing are constant. It's what's happening to the y. Some of the confusing part is that when we give our answer, where is the graph increasing, we don't report. We're looking for where the y's are increasing, but what we report is the interval of the x's that make that happen. And again, that wasn't something I picked up on ever until I started having to teach it and then explain it. But so we're looking at the y's, but we're reporting what x values make that happen. Okay. So always use X intervals. So that's the first thing is we're reporting what's happening to the X values. Again, X's are always increasing, but we use which of those X values cause or is the Y increasing or decreasing or being constant. Use open intervals. So the idea is at the endpoints, there's different ways to define it, but at the endpoints, it's really neither increasing or decreasing because that's where we're starting, right? To be increasing or decreasing, you need to have a point before it and a point after it to see what's happening, right? So at the endpoints, well, that's a starting point. That point itself has nothing before it, so we can't say whether it was increasing or decreasing. And the last point has nothing after it, so we can't really characterize it. So we want you to use open intervals, what we call, so those are parentheses. The endpoints are not part of the discussion. Okay, it just makes things easier. So, and then, as was brought out, always look left to right. So on this one, this example, we would say if we're looking for the parts that are increasing, what we're going to look for is where the Y's, again, we're going to read it from left to right, so we're looking for where the Y's are increasing, increasing, increasing. And so what we would report here is that, so when we have this arrow, it means it's going down towards negative infinity. It also is slightly this way, so what we would say is it's going from negative infinity. The x's are going from negative infinity. Over here, the x's go to positive infinity. So from negative infinity until -4. So notice I'm reporting what x values cause the y values to increase. So we list that as negative infinity to 4. Use a parentheses because, again, at 4 itself, it's neither increasing or decreasing, or actually that becomes a turning point, right? So on one side, on the left side, it's the function's increasing to get to 4, but after 4 it starts decreasing. So that's why we use this this open interval, because at 4, what's really happening? Well, 4 itself, it's a maximum, as we're going to see. It's a different type of thing. And then we've got this gap where it's decreasing, and so what we indicate that with is with interval notation. That's where we use the U for union. There's a big open space, but then it increases again, and that's going from x equal -1 until x equals +1 is another area of increase. And then we have this open area here where it's decreasing again, so we put our union, and then we're going from x equals 3 until positive infinity. So that's the way we would list an interval of increasing values. And remember, what's increasing is the y values are increasing, but notice what we're reporting on these intervals is what x values cause, or where the y values are increasing. And we could see that the decreasing values, at least in this one, because we don't have any constant areas, are going to be the areas in between. So we would go from 4 to 1. That's a decreasing interval. And then we have this union part, and then again going from 1 to 3. So that's kind of this area here. And you'll see mostly with polynomial functions that happens. It's either going to be an increasing or a decreasing area, and we've got these sort of holes where it's not increasing, that means it's decreasing. And then for this we have constant. There's no place it's constant. So for this particular one. So those are the types of things we're going to report about graphs. And that gets us into, as we go towards calculus, we need to be able to see graphs in this way, because calculus is about rate of change. And so if it's increasing, that's a positive rate of change, so we know we're in an area of positive rate of change, and that's what calculus is all talking about, is the rates of change. So we start looking at graphs in terms of how are they changing. Okay, are they increasing? Are they decreasing? And remember, what we're focusing on, the change, is the amount of change in y, primarily. X is always going to be increasing what's happening to the y. So then, along with that, increasing areas, decreasing areas, constant areas, what we saw is when we went from an increasing to a decreasing area, what's always going to happen? Or pretty much, right? You go up the mountain, you get to the top, you can't go any higher, right? You have to start coming back down. So we get a maximum, we get a summit as we go up the mountain and come back down the other side. Same thing happens in a valley. We go down until we get to the bottom, can't go any lower unless you dig some holes or something. You got to come back up out. So that's what these maximum and minimum are. So there's the top values. And so as we identify the areas where it's increasing, decreasing, we were also, in a way, finding these places, which we can also call them turning points. So they are extremes, but you'll also see this term used, turning points, because it's where they change, it changes from increasing to decreasing or decreasing to increasing. Okay. And again, this is an important thing in calculus. If we know it's increasing and then decreasing, we just know the rate of change does that, we know we're going to get a maximum. Because we went up, and if you go up, the only way to do it is to come back down. The only possibility is to have a maximum. You can't have a minimum. If you're decreasing and then you increase, again, the only thing that could happen since you go down and come back up is to have a minimum. And so a minimum, a maximum. And we can call these, there's kind of different types. This one we're talking about a relative maximum or minimum. What that means is in the neighborhood, in whatever close by that area, it's the biggest, it's the highest value or it's the lowest value. It might not be the biggest value in the whole graph. And notice this max is not, because this is going up to infinity, so the maximum is infinity, right? It's going to shoot up to infinity. So there is no absolute maximum in this case, because it's always getting bigger, but there is this relative maximum here. And a good way to report a maximum is by its actual coordinates, right? Because a maximum is a point. So if we look at the maximums, we can list those as ordered pairs, -4, 2, and this is also a relative. No, it's a lesser maximum, but it is a relative maximum because in the area of where it's at, it's the biggest value. And so that is, what is that? That is 1, 0. So those are our maximums, our relative minimums, -1, -2, and this point here, 3, -1. Now sometimes, and I'm more familiar with how Alex phrases these questions. My math lab, I'll become more proficient at it. But there's sometimes when they ask this question, they don't ask for an ordered pair. They ask for two types of things. They ask for what's the value of the maximum and what's the location of the maximum or minimum. So those are code words. One of those is an x value, one of them's a y value. Notice I use the value in both of them. When we're talking about a maximum value, which one are we talking? Are we talking about the x or the y? Good. So that's the, and again, we could go either route, but the value is, the maximum value is the function value, that's going to be the y. The location is where it's located, and whenever we're talking about locations with graphs, what are we talking about? X values. So it's really important to keep those concepts clear. That there's, again, graphs are kind of easy. There's two things. It's either X or it's Y. But it's also so easy, especially those of us who are a bit dyslexic, to switch those around, and then you get everything wrong, right? But it's cool because that's what I found is when I was really struggling with graphs, and I struggled with reading graphs, and I figured out my problem was as I was mixing them up. I was just looking at it backwards. I was reading it from right to left instead of left to right. And as you'd make that one change, everything was beautiful after that. So a lot of times in math can be one of these things where it's real frustrating because we're getting everything wrong. I always say that's great that you're getting everything wrong because it's probably an easy fix. Switch one thing and then now everything goes from everything wrong to everything right. Okay, so this is going to be our x values. Okay, so just watch for that, and sometimes the way they phrase the questions, but just say, are they asking for a location? I need to give them an X. Are they asking for a value? That's a function value. I need to give them a Y, or an output. Okay, when we go to graph piecewise functions, and I'm going to show you Desmos does a real nice job of actually producing the graphs, which is oftentimes a good, you might not have to do the graph, but a lot of times if you're doing a homework problem or any problem, it may not call for you to look at the graph, but if you can look at the graph, a lot of times it'll make the concepts more clear. You might see it, think it, but a lot of times, at least for me, it's kind of abstract until I look at the graph. So we'll do both. So we're going to graph this piecewise function. The key part is with these, I'm not sure if I mixed, did I talk about algebra being from the Arabic? Okay, good. So this is the class I did it. So remember, Arabic reads from right to left. And I studied Arabic for a year. That was 30 years ago, so there's only a few words I remember, and I can't write it anymore. I used to be able to actually write it, but it does write in the other direction. But what it did for me as a math teacher is I actually looked at some of the Arabic algebra texts, and you see that the functions are written the same as they are in English. So the English, when they translated over, they didn't translate the functions, but you can see in Arabic they were reading it this way, so they saw this part of the function first. When we read from English, we read it the other way, and that's why, especially with these piecewise functions, they can be very confusing because we're typically coming this direction. We're saying, well, there's the function, x squared plus 1, but what we have to do is define where is the location of that function, and that's the second part. So that's really what we need to look at first is the domain. So what this is doing is it's saying that when x is less than -2, so we come to -2, oops, that this is kind of like a dividing point. So there's one piece of the graph is everything less than that. The other part of the graph is a part greater than that, right? So that's really what we want to look first at when we look at piecewise functions. And then we're going to, over here, we're graphing x squared plus 1, which is kind of hard to do just by itself. Graphing a quadratic, it would be something over here, right? X squared plus 1 would look something like this. And what we want is we just want this part, so what we want to do is erase all of this part. And then 2x minus 3 is a linear function, so I know it's going to cross at -3. That's the y-intercept, right? It's got a slope of +2, so it's going to be going up. So it'll be something like this. Let me erase that part, not everything, but. And so this part is not included. This has the included part is here. And so there's kind of what the graph would look like. And what I'm going to do is I'm going to show you how you can graph it with Desmos. You can do this with a TI-84 calculator. You can sort of restrict the domain and graph piecewise functions, but I've done it. But then I forget, as soon as I do it, I forget how to do it. It's got a real specific syntax. Over here, I typically forget as well, but I can usually pick it up pretty good. So we want f of x equals, what was it? It was x squared plus 1. And what you see is what I was drawing, the parabola raised up from 0, 0 to 0, 1. We'll talk about this as a transformation. But there it is. But we only want this to be from -infinity to 2. So let's see if I can remember how to do this. I think I just need this bracket, and I think I just put x is less than -2, and I put the other bracket. So just as simple as that, and I've got my piecewise function. I've got that piece, right? That's what I was trying to draw by hand. But see, this is kind of when you can kind of see it, it's helpful. And the syntax is fairly, once you remember it, is not too hard to do. I had to look it up online, and so then I'll do g of x. So thinking of this as a second piece, it's really one function, but it's in two pieces. So we have to kind of do it this way. What was it? It was. Thank you. 2x minus 3. And again, it draws the whole graph even over here, which we don't want. We want to limit this domain to be, again, curly brace. This was x greater than or equal to. I'm going to hit the equal key, and it does that. Also with Desmos, you can click down here, and you've got your symbols and stuff. We'll put -2. We'll put that, and where did it go? Oh, I put in an extra parentheses. So syntax is important. So if you're in computer science, you understand that. One of the things it doesn't do is that this is the solid dot. That's the open dot. I found a way you could actually do this. So this point here looks like it's going to be -2, 5. So what I can do is I can put in -2, 5. I'm going to change the color, and I'm going to make it an open circle. So you can get these to be as accurate as you want. Again, if you're writing a paper, maybe you need to do this, doing some research, but maybe for doing it. But just, again, for our purposes, since -2 is not included on the lower half, it's an open circle. And then, let's see, this point here is -2, 7. -2, actually -2, -7. And you can see it plotted as a solid dot, but maybe I want to make that blue. So I click and hold on it, make it blue, and I want a solid dot there. So now my graph is very accurate. So I can see it a little bit better. I can kind of zoom out. And that's what our piecewise function is. So a quadratic part and a linear part. So if we ever have to use, draw a graph or something, I'm becoming familiar with what's in the homework. We'll go through that, and what I'll do is after class in the afternoon, I'll take a look, and if anything I see that I sort of missed, I can make some videos and I can post those as well. Whenever I post something, you'll see I'll put an announcement. So even when I do get the like this lecture notes or the lecture video, once it's posted, I'll put out an announcement. So that's the key part, is you need to make sure that your Canvas is notifying you, and there's a way to set up so that it emails you. But it hopefully is going to the correct email that you're using. If you don't use your ASU email account regularly and you're only using a personal one, you're not seeing those. You can always go into the course and just click on announcements, and you'll see anything that was sent out. But check it regularly. I usually have this problem over at the community college where I teach, and if I have to cancel class, I'll put it out on an announcement, but nobody ever checks the announcements until afterwards, and they've been waiting for 15 minutes for me, and I told them I'm not going to be there. So same thing will happen here. If I can't make it, I will put out an announcement in the morning. So that's another good reason to have it. I rarely miss a day, but hey, I'm human. I'm not the man of steel. So even he got sick, I think, right? Superman got sick sometimes. So we all do. All right, questions? Okay, so you may not need to use this, but it's like I said, it's a good tool, and it's helpful just recognizing that we put the function in first, but really the important part is this domain part. What part of where's our pieces at? It's certainly an important part. All right. Symmetry of graphs. So we talked about graphs so this is really just kind of a nuts and bolts of graphs. So there's all the different things that it can be. It can be increasing, can be decreasing, can be constant. We've got minimums and maximums. We've got piecewise functions, so sort of limited domains of where something's happening. Okay, so that can happen. And then now we're going to talk about graphs can have different types of symmetry. And there's two main types of symmetry that we're going to talk about. One is called y-axis symmetry. It's also called even symmetry because this definition one is the x squared, right? A parabola has perfect symmetry around the y-axis. At least this one does. So the y-axis cuts it in half, and that will happen whenever we have what we call an even function. So we call this even symmetry. We also call it y-axis symmetry because that's the same thing. The y-axis is cutting it in half. So the left half and the right, if you were to fold them over, they're the same. Okay, so that's one type of symmetry, and we'll see it mathematically gives us a few different things. The other type is called either origin symmetry, because you can kind of see it as it passes. It's not left and right sort of symmetry. They're not the same. But if you were to think of it as a spinner, like for a game, and the 0, 0 is like where the pin is, if you were to spin this 180 degrees, it would land on itself. That's the kind of symmetry we're talking about. So sort of a motion. I call it symmetry, spinner symmetry. They call it origin symmetry. And you'll see this is an x to the third power. That's also called odd symmetry because anything with an odd exponent can make this happen. X to the third, x to the fifth, x to the seventh. So odd symmetry is another word we use for this. Those are the two main ones we're going to take a look at. And they tie in with even and odd functions. So even functions produce even symmetry, y-axis symmetry. Odd functions produce odd symmetry, origin symmetry, and so forth. So even functions, the key part is we will know it's an even function if all the exponents are even. Okay. Now I guess there's a third type of symmetry which is not really a symmetry. It's they've got neither symmetry, and so something without symmetry is neither even nor odd, and that will happen in a polynomial if we have a mix of even and odd exponents. So one way we know we have even symmetry is all the exponents will be even. Okay, so x squared, x to the fourth plus x squared, that's even. And plus, let's put this plus 3. If I put this plus 3, what does that do to the, can anyone figure, what's that going to do to the function? Okay, so you're already looking at the next section. We talk about transformations. That's exactly how so it was shifted up by 3. So will that still have, if it's got y-axis symmetry and I move it up, will it still have y-axis symmetry? Of course, yes, it will. The way we want to think of this 3, though, is it's like 3x to the 0 power. Okay, because x to the 0 power is actually 1, so it makes it disappear. But what is 0? Is 0 an even number or an odd number? It's even. So it helps us understand that this is a function that has all even values, that all even exponents. It's got this invisible one. It's really just we write 3 and it's got the invisible x to the 0 power. But that's going to help us when we talk about the next type, which are odd functions. Odd functions have to have all the exponents have to be odd. Okay, so we could have x to the third. We could have x to the third plus x. And it doesn't matter what the coefficients. This could have been like 2x. The coefficient can be even. But what we're focusing on is the exponents. So 3 is odd, 1 is odd. But what would happen to this if we added, say, 3 over here?
Neither odd nor even.
It's now neither because it's got 2 odd exponents and 1 even, because this is really 3x to the 0, right? And you could see, as we talked, the same thing would happen. This one that has origin symmetry, so it's symmetric about the origin. If you move it up 3, is it still going to be symmetric about the origin? No, you've moved it, so it's blown it, right? It's probably symmetric about 3 now. It's got the same shape, but it's not symmetric about the origin anymore. So this is not an odd function because it's got one that has an even. But again, those are the ones that throw us off because you just see the plus 3 and you don't know. I don't see an exponent, so I don't know whether it is. The other ones that throws us off is this x, because it doesn't have an exponent either, but really it's x to the 1 power. A lot of times I will write these things down. If I see x, you may see me write x to the 1 power just to emphasize there is an exponent there and it's 1. And you'll see me from time to time write this x to the 0 for 1, so just so that we know that there's always an x there somewhere. This oftentimes it's invisible. Yes?
Does it matter if there's an exponent like over something that isn't
That would not, because, good question. So if we had 3 to the second power, say x to the third, what's that? The 3 is a constant. If you square it, you're going to get 9. You just get another number. So it's just what affects the graph is the exponents on the variable itself. Good question, though. I like that one. Good. And I was able to answer it. Sometimes I'm not able to answer because I haven't thought about those types of things, but that's good. So is that kind of, again, we're going to talk about symmetry, and when we have symmetry, it makes solving problems easier, because you'll see when we have this sort of symmetry, with even symmetry, if you have a negative x value and a positive x value, so -1 and +1, they have exactly the same y value. And the same thing, -2, x is equal to -2, x is equal to positive, they're going to have the same y value if we've got an even function. So if we know we have an even function, we know it's going to have this sort of pattern. If we know we have an odd function, the opposite is true. So if I've got -1, if that's my x, then my y is -1, and if I have +1, my x is going to be +1. So they're the same absolute value, but their signs are different. The y values have different signs because one's up high and one's down low. That's how we get that's how we get that symmetry. Okay. Same thing would happen with -2 and +2. They will have the same absolute value, whatever numbers there's the same, but one will be negative, one will be positive. But it helps us analyze things if we know it's an odd function. Okay. Some examples. So is this even or odd? Think for a moment. Even? Everyone say even? Why is it even? Okay, good. Because that's at +3. That's really, again, as we were talking this, if we were going to think of it, it's x to the 0. So they're all even. So it's an even. Good. How about this function? It's a neither, because we've got an odd. This is an odd, but this is an even, so it's a mixture, so it'll have neither symmetry. Good. And that's it. That's it for this section. It should be enough to get you started in. I apologize, I have not gone. Usually what I'd like to do is go through and work all the homeworks. I've taken a quick look at some of them, but this should at least get you a start. But there might be a few questions in there that say, we didn't talk about this. But hopefully the conversation gives you enough to think your way through it. And remember, we can always ask questions before or after class or during class as well as we move forward. Okay? But do you feel like, hey, I could handle different graphs, increasing, decreasing, constant, but maximum, minimums, symmetries? That was pretty much all we talked about here. Okay. And we started to drop into it. So what I'm going to do right now, this is about 38 minutes. I'm going to stop the recording.